Uh, Good afternoon, class. Welcome to the last presentation from the chapter Colligative Properties. And here today I am with the topic osmosis and osmotic pressure, that is pi. First, let's define what is osmosis. Osmosis is defined as flow of solvent through semi-permeable membrane from a solution of low concentration to solution of high concentration. So it is very important for us to note down the moment the flow of solvent is usually from solution of low concentration to solution of high concentration through a semi-permeable membrane. This is a diagram just to understand it. This side we have the concentrated solution, here we have just the solvent. So this arrow indicates the flow of solvent from low concentration to high concentration, and here is the boundary that separates these two solutions. The flow of water will be from the solvent towards the solution because the solvent have higher water potential than the solution since it is pure. Basically, in biological systems, the solvent is typically water, but osmosis can also occur in other liquids, supercritical liquids, and even gases. Let's see some types of solutions. Isotonic. In isotonic solution, two or more solution in contact will have the same concentration. So here there won't be any osmosis taking place. The concentrated solution is called hypertonic as it has higher osmotic pressure. If it is having higher osmotic pressure, we call it as a concentrated solution. The less concentrated solution is called hypotonic as it has lesser osmotic pressure. Now this is all about osmosis. Now let's see what is osmotic pressure, that is pi. Osmotic pressure is defined as the hydrostatic pressure which is built up when the solution is separated from the solvent by a semi-permeable membrane, and it is just sufficient for stopping the osmosis process. So it is just sufficient to stop this flow of solvent from low concentration to high concentration. It is also defined as minimum excess pressure which must be applied in the solution to prevent the entry of solvent molecules through semi-permeable membrane. So we can apply some external pressure from here downwards so that the solvent cannot come this side from low concentration if we apply pressure from here. Let's see next topic, Bancroft theory of dilution. What is this? According to this theory, the osmotic pressure pi of solution varies with concentration and temperature. So it depends upon concentration and temperature of the solution. Bancroft-Boyle's law states that osmotic pressure pi of a solution at constant temperature is directly proportional to its concentration in moles per liter. So we will be deriving the equation using the following conditions. According to Bancroft-Avogadro's law, osmotic pressure is directly proportional to number of moles of the solute. According to Bancroft-Boyle's law, osmotic pressure is inversely proportional to the volume of the solution. According to Bancroft-Charles law, osmotic pressure is directly proportional to temperature. We have equation 1, 2 and 3. We will combine all these three equations. Combining equation 1, 2 and 3, we get pi is directly proportional. That means osmotic pressure is directly proportional to number of moles into temperature, whole thing divided by volume of the solution. Equation 4 can also be written as by removing this proportional sign and putting constant. Pi equals to RT and over P, where pi is the osmotic pressure, R is the gas constant having 0.0821 value. Is absolute temperature, it should be in Kelvin, number of moles of solute, and the volume of solution in liters. This condition is very, very important. Equation 5, this pi equals to RT and over P, that is equation 5, is known as Bancroft equation, and it is for solution which contains n moles of solute in the liters of solution. In concentration terms also we can rewrite this equation. Concentration C of a solution is measured in moles per liter. So C is equal to n over V, number of moles per liter, V in liters. Equation 4 can also be written as, so in place of n over V, we can directly substitute by writing C. So osmotic pressure pi would be equal to CRT. So osmotic pressure is also a colligative property, and it depends only on number of molecules or amount of solute present there in the solvent. It is used to determine the relative molecular mass of the substance. Now, moles of the solute, the substance usually N is calculated by weight of the substance in grams divided by molecular mass, so W by M. Equation 6. Now we will substitute this equation 6 in earlier case equation. Substitute the value of N from equation 6 in equation 4. We get osmotic pressure is equal to RT N over E. So in place of N we will be writing W over M. Y is equal to RT W M. Simplify this and we will get equation 7. So this equation 7 is the one, or equation 4 is the one. These two equations are important from this topic that we will be using for solving some numerical problems. The osmotic pressure of given solution can be determined experimentally by Berkeley and Hartley's osmometer. So these are the techniques used to measure that. Let's see numerical problem. Osmotic pressure of a solution containing 2 gram of a protein per 300 centimeter cube of solution is 20 ml Hg at 27 degrees Celsius. We have to calculate the molecular mass of protein, and value of R is given as 0.081 liter atmosphere per Kelvin per mole. Following informations can be obtained from the question itself. Now using Y equals to RT W M V, we can simplify this, make N as the subjective formula, and we write the equation like this. Substitute and we get the value 6315 gram per mole. Please go through these two solved examples as well, and if you have problems, please don't forget to drop down into classroom comment section. Thank you.